Right. We were doing partial differential equation, boundary value problems in different coordinate systems. And this is the last coordinate system we're going to cover. In this case, it'll be spherical coordinates. Before we did polar coordinates and we did cylindrical coordinates. Now we'll do spherical coordinates. Here's the example we'll use. This three-dimensional Laplacian in rectangular coordinates. Your function would be a function of x, y, and z, or it should be a z there. X, y, and z in rectangular coordinates. And if you go through these substitutions, these are spherical coordinates. This kind of shows geometrically how they're defined. You have a new x and y and z in terms of r, theta, and phi. And if you go through a very painful, tedious chain rule exercise, this equation becomes this equation in spherical coordinates. It's a function of three variables. And when you go through the product method and separation of variables, I should have mentioned this before. If you really do the problem in three variables, you're going to get two different separation constants. Our separation constant has always been plus or minus lambda. But if we went through this with all three variables, we'd need two separation constants. It would be a good exercise to go through. But we're not going to do that. Like before, we're going to assume radial symmetry so that this E here, which is the azimuth, I guess you could call it, any point in the sphere, it's going to have the same value for all phi. Same theta and r. And if you do that, you have this somewhat simpler partial differential equation. So let's start working on this in separating variables. Here's our equation, and we'll do the boundary value problem of the heated sphere, which obeys this Laplacian equation, and we'll say out on the outer edge of that sphere, where your r is equal to the constant, which is the radius of the sphere, that the temperature is held at some function of theta, angle from z axis. So theta goes from 0 to pi, North Pole down to the South. So we can separate as usual. U is a function of big R and big theta. Plug in all those terms. Let's see, this guy's going to be R double prime theta. This guy's going to be R prime theta. This guy's going to be R theta double prime. It's going to be R theta prime. All those substitutions, do a little algebra. Multiply by r squared over big R, big theta. That gets you to here. At that point, you can separate them. I'll set them equal to minus lambda, our separation constant. We get these two ordinary differential equations. They don't look that pretty. This one is a particular Cauchy-Euler equation. And we have the solution to that, general solution to that. That would be something we tuck away in our formula sheet. This guy is pretty weird looking, so we're going to do some more work on that guy. And the real work is this substitution. We'll say x equals cosine theta. Then you do some chain rule stuff. Variable substitution, and I'm not going to go through all this. It's a little tedious right there. And you can rewrite that equation this way. So now here are our two ordinary differential equations. This first one is a Cauchy-Euler equation with a known solution. This guy is the Legendre equation. Except our x is going to be cosine theta, but we can still use the Legendre solutions. So now let's get into applying conditions. Here's one of those implicit conditions that the solution must be continuous and continuously differentiable. That only happens when the lambda in that equation is this n times n plus 1. We make it the Legendre equations we saw earlier in the course. So that gives us our eigenvalues. Other implicit condition is that the solutions must be bounded over this interval, theta from -1 to 1, or actually cosine theta from -1 to 1, right? Or x, well, same thing. X has to be between -1 and 1. And that condition only occurs with the Legendre polynomials. Remember, there's two particular solutions to the Legendre equation. One is the polynomial. The other was that infinite sum, but it's not bounded at these endpoints of this interval of convergence. That leaves us with the eigenvalues and the associated eigenfunctions, all in terms of theta equation. Then we use the same eigenvalues for the R equation. So this would be the R equation with those eigenvalues. We have a canned general solution for that. And again, our solution must be bounded. And this guy is unbounded. So we have to set C2 to 0, and we're just left with R to the n for the R solution. So now we've got everything. Our U sub n is going to be this P sub n times R to the n. Sum it up over all possible n's. And here is our general solution with these yet to be determined coefficients, a sub n's. Here's where we apply the explicit boundary condition. That's out at where R equals C. R equals C, we've got that. And that has to equal the function they gave us, that is the explicit temperature on the surface of the sphere. How do we do that? We need to expand it in something that looks like this. That's the Fourier-Legendre series, Fourier-Legendre series, where we use cosine of theta as the argument. So we expand our function. Well, here's how in general you expand any function, big F. You expand it this way, and here's how you calculate those coefficients. We had to do some variable substitution. Recall the coefficients for Legendre polynomials, or the Fourier-Legendre series, in terms of x. Here we need it to be in terms of theta, so we had to do some variable substitution. So that gives us a complete solution, right? But we have to match coefficients. Big A sub n, C to the n must equal these little C sub n's. So that's this is matching coefficient. This all comes from the coefficient formula for Legendre polynomial, the Legendre series. So here finally is the solution summary. I'll get into a couple things you can look at. That was kind of the deriving this solution for the heated sphere problem. This is one way to express it all in one fell swoop. And we'll get into a couple of interpretation for application to this. One more recording, and then we'll be done with this sort of module.